Hello, my name is Ian Wallace, and today I will be going over the paper titled Chipyard, Integrated Design, Simulation, and Implementation Framework for Custom SoCs. I will start by going over the background and the motivation behind this paper. Modern SoCs are becoming increasingly complex to design and develop because they contain a large quantity of specialized IP blocks, such as multiple processors, different types of accelerators, and analog blocks. This increased complexity makes integration, verification, and implementation of the SoC much more challenging. This ends up making SoC development for smaller teams significantly harder, such as those in a research environment. Hardware generator workflows currently exist, for example, to generate single RISC-V cores. However, there's not currently a solution for the generation of an entire SoC. This leads to the problem statement for this paper, which is that there is no existing framework or platform that supports the following features. The first of which is a workflow that supports the integration of both parameterized open source IP blocks as well as custom RTL. Next is a workflow that supports the ability to bring the integrated IP blocks through the ASIC physical design flow. And finally, a workflow that supports seamlessly switching between different ASIC process nodes and vendor tools. This paper introduces the Chipyard framework as a proposed solution to these issues. The Chipyard framework includes a variety of features to improve and speed up the SoC development process. This includes the ability to generate an SoC design using a selection of parameterized IP blocks, the ability to generate both software-based test benches and perform FPGA-based emulation of the design, the ability to bring the generated SoC design all the way through a back-end physical implementation flow, providing the user with a manufacturable GDS2 file, and generating software binaries for the SoC. In the next few slides, we will go over each of these features of Chipyard in more detail. This slide shows an overview figure of the entire Chipyard framework. We start from the top of the diagram with the RTL generation. This shows the choices the user has in terms of the IP available, such as the RISC-V cores and the accelerators. The next section shows the RTL build process and the translation of the high-level chisel description of the design into the intermediate fertile representation. This is followed by the three branching paths. The leftmost path shows the verification flow, the middle shows the flow for generating software for the SoC, and then the rightmost path shows the automated VLSI physical design flow. The first feature of Chipyard we will cover is the IP block generation and SoC integration component. Chipyard utilizes the open-source Rocketchip SoC generator, which itself uses the Scala-based Chisel high-level abstraction language. Rocketchip allows the user to select what IP they want included in the SoC, and the tool ensures that all of the parameters and interconnections are compatible across all of the IP in the system. Additionally, custom RTL is supported by Chipyard. All that is needed from the user is to provide a chisel wrapper, and then Chipyard converts the chisel source code into an intermediate representation, which is called fertile. This stands for Flexible Intermediate Representation for RTL, and it is a bridge between the high-level chisel language and the lower-level HDLs like Verilog. Fertile is used by Chipyard for driving the different supported flows, such as verification and physical design. On this slide, we have a simple example showing what the chisel language looks like. In this case, we are specifying an SoC with a RISC-V processor and a SHA-3 accelerator. Next, we will discuss the ability of Chipyard to generate simulation test benches for the generated SoC. Software RTL simulators are critical for verifying the functionality of a design, and writing RTL test benches is often a time-consuming engineering task. Chipyard outputs makefile scripts which then generate simulation executables for the chosen simulation tool. Chipyard supports generating outputs that target both open source tools such as Verilator and commercial tools such as Synopsys VCS. Another key component to the Chipyard simulation toolbox is the ability to support FPGA-accelerated emulation by using FireSim and the FPGAs available on AWS. FireSim itself is an open-source FPGA emulation tool that provides many of the same features as commercial equivalents. Once again, Chipyard takes the fertile representation of the user's SoC design and generates the scripting and code needed to perform FireSim emulation of the design. Next, we will go over the back-end physical design features of Chipyard. Chipyard uses a modular VLSI flow called Hammer. Hammer takes the fertile representation of the user's SoC and generates PDK-specific and tool vendor-specific outputs, such as tickle scripts, clock constraints, and power constraints. These outputs can then be consumed by the targeted vendor tools, such as Synopsys Fusion Compiler, in order to generate a manufacturable GDS2. Hammer uses a hierarchical physical design flow for implementing the user's design. This is well suited to the IP block-based design of an SoC and tends to lead to higher quality outputs that are emitted by the EDA tools. Hammer currently supports a fixed number of PDKs and backend tools, including an open source PDK called ASAP7. Once again, this demonstrates the appeal of a tool like Chipyard for smaller teams and academic users. For larger teams or those in commercial environments, Chipyard supports adding other PDKs and targeting different vendors by creating Hammer plugins. Finally, we will go over the software workload generation features of Chipyard. Chipyard uses the Fire Marshal tool for automating the generation of Linux-based and bare metal workloads. These workloads can run on RTL simulations and FireSim simulations. This allows for the verification of functionality and the performance of the SoC. This feature of Chipyard allows for the software development to ramp up quickly, even if the hardware changes. On this slide, we will go over some of the main limitations that currently exist with Chipyard. One area in which Chipyard is lacking is in the analog domain. Chipyard currently does not have support for generator-based analog mixed signal IP blocks. Analog designs are more coupled to the PDK than digital HDL designs, making designing process-independent analog designs a challenge. Generator-based analog designs are an active area of research, with tools like the Berkeley Analog Generator currently under development. Another limitation of Chipyard is the challenges faced with the wide-scale adoption of open-source tools like those used in Chipyard. This is especially true within the commercial space. Modern process node PDKs are tightly integrated with commercial EDA tools and their associated scripting. It's this PDK scripting interdependence that may be challenging to decouple, as would be required by the Chipyard framework. This might make adoption of Chipyard by a commercial team difficult, especially if they have an existing, fully developed VLSI flow. Finally, we have the overall conclusion for this paper. Chipyard is a framework for generating an SoC using reusable IP and bringing that SoC through simulation, FPGA emulation, and back-end implementation. Chipyard is designed to simplify and accelerate SoC development, and the fully open-source nature of Chipyard is ideal for smaller teams and those in an academic setting. The adoption of Chipyard by larger teams in a commercial setting may be more challenging. However, overall, Chipyard promotes a modern, reusable, IP block-based design process. On this slide, we have the references and links to the papers for Chipyard, Hammer, as well as the Chipyard documentation. And then on the bottom here, we have a statement on generative AI, which was consulted when creating this presentation. Specifically, I used the GPT-4o model.